Okay, in this video, I'm going to discuss Codesys, kind of just take an initial view at some of the files, folders that I have in the source code. Probably discuss a little bit some of the basics of Codesys, perhaps, and then kind of look at adding Ethernet devices for I/O. So we'll go ahead and open up Codesys program here. So when you first open up a Codesys project, you'll likely see one of these tabs open. So the devices tab basically allows you to designate different hardware that you want to include in your project. So at the very top level, we have our PLC device, which is the um, Control Win V3. That's our soft PLC running on my local laptop here. But you can change the device that you're talking to by clicking that update device. So for example, if I wanted to talk to a Raspberry Pi, I would come down in here and click on this Raspberry Pi controller. But since we're using a Control Win x64 version, this is what you want to choose for the industrial PC. Other things to note on this page, symbol configuration. This is what allows us to designate data tags to our OPC UA server so that things like our UI OPC UA client has access to our internal variables in our code. And so we can determine from our symbol configuration which variables we want to share with the outside world. So it's not necessary to share everything. So that's why only select items are selected here. So for example, I have this machine global variable that I'm sharing everything in there. Anything in the main program, I'm sharing everything in there. We're probably not using most of this, but it's an easy catch-all for me, so I don't have to modify this. And then the settings tag here I'm also using. So anytime that you want to make modifications to the data that you're sending over, good idea to pop open symbol configuration. A lot of times you'll see the check mark is not a check mark, it's a dot if you changed something about the machine variable type. And so it'll basically force you to check, explicitly check the data that you want to send. A lot of times I just uncheck and recheck, and that solves it. And then you typically want to build this. Anytime you make a change to symbol configuration, you run this build, and that will make sure the next time you download that the OPC UA server is updated properly. So other things to note, our task configuration, this allows us the freedom to kind of designate different frequencies or cycle rates at which we want to run some of our different programs. And so our entire program is housed on this main program POU. And so anything in our source code logic that's running the conductor code, the robot device code, anything like that is all being called out in our main program. But aside from that, there are other tasks that involve calling things like our Ethernet IP devices. And so our Codesys program has a Ethernet IP scanner. That's what we use to talk to all of our different devices inside of the side of the project. So we have, just getting rid of some of these old things that we don't use anymore. So in our device tree, Ethernet device tree, we are talking to all sorts of Ethernet IP adapters. We got a FANUC robot controller. We've got the SMC valve IO module. We've got the pills controller Ethernet IP module, and then the CNC controller module. So all of these items we communicate over this Ethernet IP protocol, and we establish ourselves, we being the PLC, establish ourselves as a scanner, and as a scanner, we look for specific IP addresses in the world that we want to talk to. So for each one of the devices that we have listed, there's a certain frequency or RPI at which we want to read data, and ultimately when we decide to scan in and refresh our inputs and outputs from these associated devices, that's all happening here. So this this little program here is actually responsible for making sure that that happens on time. I haven't personally dug in very deep on how that all works, but effectively, you can change the cycle. So this task, for example, scans every 10 milliseconds. So if I needed something faster than that, and I wanted to have a faster RPI, I would have to adjust my scanner rate here to be something lower than 10 milliseconds. Sometimes it's necessary in certain programs to have instantaneous input and output reaction. So had if you had some high speed, quick response need for a particular application, like let's say you were trying to detect some position of some label on a high speed roller and you were detecting it with an input, well, you wouldn't want to wait 10 milliseconds. You'd want to go much quicker than that, and so you could affect all that inside of this task configuration. For our main task, we're doing what's called freewheeling. So basically, as soon as we're done executing the task, we immediately start back over. So that enables us to run lots and lots and lots and lots of cycles very quickly with our main program, and we don't have to wait a certain millisecond to start it over again. So generally, that will improve your um, reaction time in your code. And one of the large benefits of using Codesys is actually the cycle time to run our main program is like it's in the microseconds, I believe. So it's very, very quick in comparison to a program in like Allen Bradley controllers. Largely, I think that's just largely due to how the code is compiled and how it's executed on the runtime. So I haven't looked too much into that either, but I have noticed that the cycle times are really quick. So that's kind of a cool feature. Um, Other than that, the library manager here allows you to include certain libraries that you may want to include in your project. For example, I added this debug logger, which is a third-party library I got from Codesys Forge. And this just allows us to create some debug log messages to an array on the PLC. So you add it typically in here. But I don't have to use this too much. But every once in a while, you got to add a library, and you add it. You come in, you select it. There's some tutorials online you could look up to see how to do this. Um, Yeah, so that's kind of the this device tree side of um, our application. I'm going to dig in a little bit deeper into some of the Ethernet stuff. So at the top level, when we define an Ethernet device, typically what we're defining is an Ethernet card. So our Ethernet card settings for our soft PLC, we've decided we basically need to tell the PLC like, hey, we want to use this local Ethernet card for me. If I was running it on my laptop, I would want to come find the specific Ethernet card that I'm using. Um, but since this is meant for the industrial PC that's running in building 1, I'm not going to mess with this. But effectively, yeah, we're just telling the PLC which port to listen on, which IP address to listen on, I should say. Um, and then there within, we can add new devices. You'll see we have an Ethernet IP scanner, so that allows us to talk to all of our Ethernet IP adapters. But it's possible that maybe there's another PLC we want to talk to. And so in that case, we would have to establish ourselves as an Ethernet IP local adapter. So we can add that device into here, and we would have to configure that and that would enable us to talk to another device. And so you can see, it adds it in to this device tree. We can configure it, but since we're not using it, I'm going to go ahead and delete it. Um, Sometimes you may want to add a non-Ethernet IP device, like a Modbus or a Profinet. You can also do that here. So that's a little bit about how to add Ethernet devices. Once I added this Ethernet IP scanner, then I had to add individual devices. So I looked at all the different adapters that I have. Um, and all these adapters are imported EDS files. So anything that is non-generic was imported as an EDS file. So typically the manufacturer of the hardware, like this Pills hardware, they had an EDS file, gave it to me. Ultimately, in the device repository, you come in here and you do something like an install. Typically, you drill down to this like remote adapter, go install, and then you go search for that EDS file, click it, click OK, open it, and then it imports it in, adds it into this folder. Um, and that's what enables you to add those devices in. So once you actually add a device, you're going to have to configure some of the parameters inside. So you'll have to tell the PLC which IP address to look for. Once you're done with that, then typically um, there may or may not be some connections already set up in here, depending on if it's a generic Ethernet device, or if you used an EDS file. For this particular example, this EDS file already had this connection name here, and then we just had to designate the output size and the input size. So this stands for object to target and target to object. Object represents the PLC, target represents the adapter, or in this case, the FANUC controller. So object to um, object to the target is an output. So that's the outputs that we're sending out, and then target to object, that's the inputs. So once we have defined connections, then we have the ability to click on that connection and modify. Basically, we can discretize or chunk up the the 12 bytes that we've designated, we can chunk it up into more meaningful data chunk sizes. For example, if let's say our output we were sending four, or let's say we were sending three real data types out, and those were being read. Well, three reals are 4 bytes each. And so rather than converting our reals into individual bytes, we could just add here, we could just add a reel, and then it automatically knows that it's 32 bits, aka 4 bytes. We could add that in there, and it would append that here. And so we could write to that real data chunk right there. But I'm going to go ahead and delete that. But yeah, you can reorganize the order in which that chunk exists in the overall chunk, which is, mapping those data chunks is something that you should have information from the manufacturer on how they discretize the data coming through. So for this example, there was a document that we referenced, which gave the data on the controller side. They had some naming convention for the different data bytes that they were using, and the outputs, or the inputs to their system, the outputs from our system, were in this 3100 range. So R3100 through R3111 was what we needed to use to communicate an output. And so once you've kind of broken up your data chunk into either bytes or integers or reals, double ints, you got quite a choice there. Then, once you're done with that, you can actually come down to this Ethernet IP IO mapping. So once we're in this section here, Ethernet IP IO mapping, this is where we actually assign, or basically we effectively alias a real data tag that exists in our program to this designated chunk of data that exists on our device. And so the way that we do that is we just double click in this field, and you can navigate to the data chunk that you're looking for by looking for it in here. In our case, I believe it was all in here. This Fanic 0i data chunk, global variable. So if I wanted to give this that data tag, I could click OK, and then now that's assigned. So anytime this byte address updates, it will copy over its value into this chunk. So yeah, you basically do that all over the place here. You can see here I assigned all these different variables right here, mapped them to the associated bits. So this byte R3300 is comprised of 8 bits, 0 through 7, and each bit represented a Boolean value. So I ultimately assigned a specific data tag to that Boolean value. So that's pretty much what's necessary. And then you do the same thing, on both the input and the output chunks. And that's what's necessary to be able to, yeah, data map, I guess. Yeah, effectively data map real data tags to your Ethernet IP device data channels. Um, so just to kind of finish out this topic, um, now that we're kind of just discussing IO mapping in general, I chose to use a global variable to write to as a data tag because it's, well, let's get into this in the next video. I think it could be longer than what I want to talk to, but um, we'll get into that next time. But let's go ahead and transition and just kind of talk a little bit about the file and folder structure for this source code. So when we click on POUs tab down here, we're going to get these different folders. But primarily, most of the source code that you're going to want to look at is going to be in this src folder, source file folder. And I have the overall system broken up into these different kind of device levels. And so if we wanted to drill in deeper, let's say into like the conductor level code, drill in and we have a subfolder here with some conductor related data types. So all these data types relate to the conductor. And then I may even break the conductor up into smaller chunks. So here I have a task planner, and then I have some associated data types with the task planner here, and associated source code. So this would be logic that I'm using within the code. So you can just kind of drill down and find, you know, generally the way that this is broken up, you should be able to take a guess at, well, is this a conductor level code, CNC code? You should be able to break in and find it in here. And there are a lot of things housed in this system folder, but it's, again, you just kind of drill down and look around. Big things to note in here in the system folder would be, like the IO map, the fault monitor. I've got the safety. I actually might move safety. Let's move it. Let's move it out here. Yeah, I've got, all these different things. So device IDs. Um, like I said, the entire code is based in this main program. So anything that's housed or ran is first called in main, and then main is actually a ladder diagram that runs and executes this code sequentially. So the first thing we call is the system config function block, and we can double click that to open that logic up. So typically this is just something that we code that we call once, but make some configuration level settings in here. Aside from that, then we come down and I kind of have the system broken up. I've got all these different kind of little helper function blocks here. Our fault monitor, safety function block. And then at the conductor level, I have this mode manager function block, and then the conductor houses most of the code. So most of the things that are interesting are going to be happening in the conductor. And the conductor is a ladder diagram. Then down at the bottom, it has some children devices. and those children devices have children themselves. So you just kind of drill down further and further until you find the thing that you need. But that's all happening here in this main program. And when you um, want to run some code outside of the main program, like for testing purposes, typically I have this test folder here, and you can write. This is just another program, and it just runs usually just some small portions of the code. So you can do kind of individual unit testing on some of your different logic. Um, Trying to think would be a good example. I had one for error triggering here. Had one for remote controlling the the CNC. So these were uncommented, and I was basically just toggling these different outputs on and off, and then looking at the inputs in this little structured program. And you can tell the overall logic here to run those programs by coming into your main task, and you add a program call. You navigate. For me, if I wanted to run a error trigger test, I'd add it in there. And depending on if the main program was going to mess with my test program, I might delete main here and only run this test program. But I think I didn't typically do that. I would usually run the test program after main. I think that kind of covers just kind of the layout of different source code I have in this packages folder. Have some kind of like reuse code. Um, in each one of my devices, I have this device data type, and then I have this device function block we'll get into a little bit later, but you could copy this code and modify it anytime you want to add a new device. Got some off-the-shelf Ethernet IP device logic, or some data types rather. Yeah, so I've got these pills, Ethernet IP inputs. Same thing with these SMC. So all the like IO, I created a global variable. And this global variable just includes these two data structures. Nothing too complex. Some helper methods in here. Something I use quite often is this device state engine. Which I may actually move to this folder. Got this debug logger. I've got this clear data function, which just basically clears a structured data type, custom structured data type. It accepts any data type, and you can just say clear data, and it will wash it away for you. This debounce signal function block is typically used for sensors. To position device. that's a generic device that I would use for an actuator, like a cylinder that has an extended and a retracted position. Typically I call it position A, position B, which corresponds to the ports on a valve. There's typically a control valve has an A port and a B port, and so when A port's pressurized, that's what I would call whatever the cylinder moves to. I would call that position A. Whenever the B port is pressurized, that's what we would call the position B. And the associated sensors to detect those positions would be sensor A and sensor B. Um, so yeah, some reuse code there. But I think that covers that for this video, and then maybe in the next video, um, we can go a little bit deeper into some of the specifics. Maybe just lastly, I'll just touch on these global variables here. I have some global variables that I want to use throughout the code, and so I define it here. When you define a new global variable, you just add an object, global variable list, and then that allows any program, any function block, any function to access that data tag without having to instantiate it. So it's incredibly useful to do it for things that you feel like would be shared in the code overall. Like I have an inputs data type that has all my inputs, discrete sensor inputs here. Same thing with outputs. Um, and yeah, settings. GC stands for our global constants. So these are things that we may use throughout the code that would change. I might just touch lastly maybe on IO mapping. I know this video is getting long, but on IO mapping, we come in and look at our source code. We go to the system IO map. Within this routine here, I I break out the Ethernet IP device and I assign it to these. I break it out to basically device IO, and device IO is a device is a it's a module of code that I use inside of the source code. So that device would be something like the safety or the robot, the CNC. So that way I can kind of take the physical device that exists out in the field, which listens to the inputs or the out and sets outputs, and I can reassign that, remap those to internal device IOs. So this is extremely helpful in just kind of organizing the inputs and outputs, because one of these IO cards may go out and you may want to like quickly remap it to, you'll figure out a new solution and remap it to the variable that you're using throughout your code. Like I'm not using this variable in the code anywhere other than right here. This is being used in the code, so this is a pretty typical strategy. Um, typically we want to separate the hardware layer from the software layer, and this is kind of where that happens a little bit right in here. So I'm doing that for the pills controller, SMC valve bank, FANUC, guess that'd be the R30 IB IO. So that's where that's happening. And I think the CNC FANUC, I think I actually, for whatever reason, chose to map that. I did not feel the need to have to remap that because this is kind of FANUC 0i function block is specific to that device, to that FANUC controller device. So it's not like I would be sharing these inputs and outputs with other devices. Like the SMC, it has several inputs and outputs that aren't just specific to like the wash. It's also the deburr. Um, it's also the CNC door. So that's why I kind of break external remote I/O modules out like that in the I/O map. But here I didn't do that. But yeah, if you just want to, you can chase, this FANUC Ethernet IP inputs. You can chase this FANUC 0i data type by just coming down again, opening up this and going to the maps. You can see this is where the mapping occurs. So that is kind of I/O mapping and Codesys introduction as a whole in general. So I'll go ahead and sign off with that.